Good morning, guys. Yeah, I know it's 5 o'clock, but yeah, we're just getting started, right? So please bear with me for the next 30 minutes. We're going to take a look at how ING is using Petri Net to model this financial organization. A bit about me. My name is Adil, and I work at ING as a lead engineer. And today in this talk, what we're going to do, we are going to take a look at a mathematical formalism called Petri Net and how we are using it to model a financial organization, ING in this case. So the outline of the talk is as follows. First, we're going to give you the problem that we're solving in today's talk. So give you a bit more context that what ING does and what kind of problem we are solving there. And then I'll give you an introduction to Petri Net just in case if you don't know about it. It's a mathematical formalism for modeling concurrency and control flow. And then we'll move on to the application of Petri Net at ING. And finally, I'll conclude with some remarks and pointers to our future work that we're planning on doing on the project. So without further ado, let's get started. ING is a global financial organization which has been operating in 40 different countries and serving around 36 million customers right now. And the way it's serving that many customers via a large amount of processes. So if you think about opening an account and think about just in Netherlands, we have 40 different products to manage our current account. And if we empirically take a look at how these kind of processes are built, we use a lot of low-level programming. In this case, it's a sequence diagram of a process communicating with different services in order to create current account, which in paper looks quite okay, but as we jump into the code, it gets quite messy as we are using quite a low-level programming in order to model this kind of processes, which is largely ad hoc, error-prone, and very time-consuming, and hardly scalable. As the system evolves, reasoning about this kind of interactions where a service communicating with many different services become much more difficult. And it also becomes quite difficult to change a service because it might have a ripple effect on other services. So proving the correctness of the modification become much more difficult as we are dealing with we are using very low level programming in order to process our models. So when we change something, it looks like and try to deploy it in the production, it looks like this. We hope that it might work, and if it works, all okay. But if it doesn't work, then we have some interesting problem that we need to solve in the production systems. In general, it is quite difficult to specify how a system should behave and ensure that it behaves according to the specification. But as a financial organization such as ING, it realizes that we need better model, tools, and technique in order to implement this kind of process where it interacts with a lot of different distributed systems in order to fulfill the customer's request. And therefore, at ING, we are moving towards building one unified platform, a bank of future, where using one platform will be serving these 36 million customers. And therefore, the platform has to be omnichannel, scalable, and resilient, fault tolerant, all the buzzword compliant. And therefore, we are moving towards service-oriented architecture, microservice-based architecture, where each services, if you think of it as a building block, it has to be a very modular building block, and at the end we'll be composing this building block in order to create a bit more complicated, complex systems. But as we start building our system as a composable building blocks, it poses some difficult challenges with respect to coordination, integration, and synchronization of services in order to fulfill a request. Let's say that you as a user want to create an account in ING, meaning that, okay, somehow we need to coordinate among different services now. For instance, in this case, if you want to create a customer, create an account, it has to go through 3 different services. And the first service here is registering a user to ING system. And the second one is just generating an IBAN number. And the third service there, open account, it's assigning an IBAN number to a customer. So that brings us to the problem that we'll be addressing in this presentation today. How we can model a process, an abstract specification of a process that can interact with different services. So we need a formalism by which one can specify a process that interacts with different services. And we have to have this ability to analyze this process so that before we deploy it to production, we somehow have this assurance that, okay, it will work. And the fast and dynamic composition of the services and proving that composition works is an essential requirement for us at ING to accelerate its time to market with diverse set of products. So this is the problem that we'll be addressing in the rest of the talk. And since it has a great value for ING, we started to look into different solutions for this problem. So we started brainstorming, we went to academia, started reading some papers, and we found a curious little language for concurrency and control flow called Petri Net, which provide a high-level yet precise language to express and reason about the concept at their natural level of abstractions. And after we did some more investigation, we found out that, okay, it's a very expressive language to model all different kind of control flow patterns. And after further investigation with reading a lot of different research papers, we realized that it's a really well-founded process modeling technique that has formal semantics. So if you use it, it's a very simple language. It has a graphical counterpart, but it has a formal semantic. So you could analyze this, analyze the specification based on Petri Net to come up with some interesting aspect of your system. So that's why they have been used to model and analyze processes in different domains. For instance, it has been used in modeling protocols, modeling manufacturing tools, and also in business processes. As you can see, there are several papers that's also pointing out to the fact that it can be used effectively in composing services and for coordination and integration of different services together. So we thought that, okay, it's a really interesting idea. Why not we do some investigation, dive into it a bit more. And in this section, I'll give you an idea that what Petri Net is, its basic construct, and its semantics as well. So this expressive power of Petri Net has been here since 1962, so it's quite old. It's around like 50 years old now. And there are only 3 building blocks of this modeling language: place, transition, and token. A place, you can think of it as a placeholder, which can contain some tokens. And there is a transition that can consume some token from a place and produce some tokens in some other places. So these are the only few building blocks that a Petri Net has. And with this building block, we can define the structure of a Petri Net as follows. The Petri Net is a bipartite graph, which is connected and as well as directed. So the node of this bipartite graph can be only only a place and a transition. And the place can have tokens as well. So distribution of token is formalized with this notion of marking. You can think of it as a function which takes a place and give you number of token that place has. Or it can be modeled with some other data structure like vector or multiset. For instance, in this case, in place P3, we have 2 tokens. So you can see that aim of P3 is 2. So this marking gives you an idea that, okay, how the tokens are distributed among the places. So now we have all the basic constructs, so we can formally define what a Petri Net is. Petri Net is a tuple of P, T, F, and M0, where P is a finite set of places, T is a finite set of transitions, so we already know about place and transition, and M0 is the initial marking, so initial distribution of token in the graph structure. And the important part here is F. F is the flow relation. It represents the arcs between a token, between a place and a transition, which in essence determines the behavior of the network. So for instance, in this case, we have a graph. We have a Petri net. The T1 is connected to place P1 and P2. Both has tokens. So since all the input places has tokens, T1 is active or enabled in this case. And when it is triggered, it consumes one token from each input places and produce token at output places. So in this case, when it fires, it just consumes some token from the input places and produce the token and output. As simple as that. So we'll dive into the semantics of Petri Net, its execution semantics, with a token game. For instance, in this case, T1 is connected to this place which has a token, meaning T1 is enabled. So when the transition fires, it just passes the token to its output place, and which in essence enables transition T2, and in essence that enables transition T3. So that's how it passes token from a transition to transition. Transition just moving token from input places to output places. And it creates this interesting relationship called causality. So as you can see, the T3 cannot be fired before T2. So it actually, you could explicitly encode some ordering in your, with Petri Net in your topology. Then there is this concept called cold transition. In this case, T0 is a cold transition because it doesn't have any input places. So it is enabled all the time. And this kind of transition are a bit rare, but it represents the event that can be fired from outside of the transition. So you could fire something from outside of the transition that can produce a token. So that's what it represents. So it models the communication outside the Petri Net into inside Petri Net. And when the token is enabled, in this case, token is in place, then it enables two different transitions, T1 and T2. Now we have two transitions enabled. In this case, it selects one of them non-deterministically. So this kind of property encodes some non-determinism. Using this, you can also also define some safety requirement in your Petri Net. For instance, in this case, either T1 or T2 will be executed, not both of them. So using this modeling language, you could encode this kind of safety requirement. This is just only one of them that I'm showing, mutual exclusion. If T1 gets fired non-deterministically, it can split the token flow in multiple branches. That can be executed concurrently. In this case, since T1 put the token in two different places, T3 and T4 both gets active, and then you do have concurrency. So you could encode explicitly how concurrently you would like to process your Petri Net. Since T3 and T4 does not have any dependency among each other, they can be executed parallelly. And so now that we model concurrency with Petri Net, there has to be some way to synchronize. As you can see, the T5 can be only enabled when both T3 and T4 is done with its processing and put the token in the output places. So in this case, by using this kind of semantic, you could encode synchronization in Petri Net. So as you can see, using this simple modeling language, we have defined several things. We could define causality, we could define concurrency, and also synchronization. And it also allows us to specify some safety requirement like mutual exclusion. So using this formalism, we thought that, okay, we could define the control flow of service interaction quite nicely. Therefore, we had a problem, and suddenly we found a formalism that we can use to solve our problem. And therefore, we thought that, okay, why not let's do a proof of concept with this formalism, Petri Net. And therefore, we started with a team of developers to build a colored Petri Net DSL on runtime. A colored Petri Net is a bit different than normal Petri Net. In normal Petri Net, you don't have the tokens doesn't have any value in it, but in colored Petri Net, the token has value and type as well. You can think of it as a domain object in your system, account or user. So we build this library that allow you to model colored Petri Net and also run it in Akka cluster. And we use a bit different transition model. In this case, the transition T takes input marking and also a state. And whenever transition is fired, it produces an event. So we were moving towards the event-driven architecture in this case. And when this event is produced, we can apply this event on state S to produce a new state. So you could think of it as a event sourcing function. We had old state and an event, we can produce a new state from it. The reasoning behind using this kind of transition model is that we thought that, okay, if we are defining process with Petri Net, somehow we need to migrate from one version of the process to the next version. So we had some notion of versioning with the state. We could do something about it. So let's take a look at an example of making pasta with Petri Net. So basically, in this case, we have a structure. We have a network structure where first we are doing groceries. It can give you pasta and tomatoes, and then we can boil that pasta and cook sauce. So T3 and T2 can be executed concurrently. And when you have boiled pasta and tomato sauce, we synchronize it somehow with a synchronization construct, and then T4 serve the dinner, and we're done with this Petri Net. We can model, in order to model this network topology, we use type level DSL. So if we just focus on this part of the graph, here we can define the pasta, the places of boiled pasta, tomato sauce, and done, using this code. And also we can have a transition that takes a boiled pasta and tomato sauce and do some stuff with it. So this is how we can define place and pasta using the DSL that we have in Pajero. And using the type level DSL, we could just specify the flow relationship. Then we have the graph, the graph above specified. But note that we have to specify all the flow relationship manually. So the whole graph can be, whole net can be described using this flow relationship. And it's compiling at the compile time. It can check all the type matches or not. So in order to do that, we use shapeless. And so this is how you can declaratively specify your network topology. But when it's done, designing the definition of the net, we can instantiate, we can materialize this net as a Petri Net, and then we can start executing by firing a transition. For instance, when we fire groceries done, we get pasta and tomatoes. Then T2 and T3 can be executed in parallel, and then when we have both boiled pasta and tomato sauce, we are serving the dinner. So basically, this is how you could design your processes. You can execute them, and you could do also some analysis on it. We'll come back to the analysis at the in the next section of the presentation. But we have seen that, okay, it's a graphical representation, it's a graphical modeling language, but it has formal semantics. So we thought that, okay, it could be quite ideal for ING, because we have expert and non-expert both are working in the same team, so they can communicate with the same graphical modeling language. And important part here is that, okay, it's a state-based, so we could do something about the process migrations. And there are a lot of analysis techniques that we'll see in the next section of the presentation that we could use. So we thought that, okay, it's quite interesting. Maybe we could use it to actually model the current account process that we already had in ING. So when you started modeling, we suddenly see that the graph structure start to grow really big. And as the system evolved further, it become massive. And we realized that, okay, it would be quite error-prone to draw all the flow relationship between the place and the transition manually. And it will not work. So we get a completely mixed reaction from from the stakeholders and developers of the team that okay, it's difficult. And yeah, we thought that it's cool, but a lot of people like, no, it's really difficult. So basically, the learning from this exercise was that the name structure grows really large for large to reason about for industrial processes. And though Petri Net is a simple language, it's an academic formalism which has yeah, formal semantics, which scares people quite a lot. Modeling and analyzing business processes is a non-trivial task, and it's kind of an art than science to model processes. So we started to think that how can we make it work? How can we come up with a better solution than the solution that we had? So we realized that okay, maybe we could come up with a bit higher level of abstraction than Petri Net, and which allow us to define those transition, and we'll give this transition to this abstraction, and it can generate the flow relationship among those transition. So basically, what I'm referring at that okay, if you have a sequence of transition, one can analyze this transition and derive that graph structure, the bipartite graph that I've shown earlier. But that doesn't solve the scary part that okay, it's a mathematical formalism, and the adoption of this formalism is very critical for our project. So we realized that maybe we can come up with a nice DSL. So we built this project called Baker. It allows you to define the processes with ingredient and create a recipe. So just like we create pasta, which has a lot of different steps. So we thought that okay, in order to define this recipe, you would define those steps, and you give the ingredient, then rest of the stuff Baker will do it automatically. So in particular, it enables orchestration of complex service-based process flow, but it will use the terminology from familiar domain like recipe, cooking, and that kind of stuff. So we started to build this abstraction. So there are like main three things in this case. We come up with ingredient, event, and interaction. So previously we cooked pasta. Now in this example we'll be cooking pizza, and we'll give you an example how this DSL works. So ingredient, like any recipe, like okay, if you're cooking pasta, what would be the ingredient? It would be like flour, tomatoes, and that kind of stuff. So those are like ingredient in our DSL as well. And more event, there's this notion of event that models causality. So you could think of it as a primitive signal, but it can carry some structured data. For instance, in case of baking a pizza, an event could be that okay, your kitchen tools are available. That event gives you a lot of kitchen tools like bowl, fork, oven, and sieve. Or it could be like only oven heated event. So let's say that you turn on your oven, you get an event that oven is heated already. So you could define this kind of events using your by extending this event marker trait, and so you specify all the stuff that it can produce. It might not produce anything. Then the last construct of our DSL is interaction. It can be you can think of it as just a function, or it just as an I/O that is communicating with an external service and give you some result. So it's an operation. For instance, if you think about sieve flour, what do you need? You need a flour and salt and sieve, and then you do something and you get sieve flour to bake your pizza. So it can be defined as follows. This sieve flour can take like 3 ingredients, and it provides sieve flour as an ingredient as a return. So we could define these interactions. But note that we didn't define any implementation of that interaction here. We're just specifying that okay, this could be an interaction, this could be a step in your recipe. Then we can give this recipe. We can construct it. We can create a recipe from it by giving all the different steps. But this step doesn't have to be ordered. So you could give this step in any order. And you would also give some external events as well. If you recall, these are equivalent to cold transition of Petri Net. So these are the events that could be fired from outside. For instance, one could be like, okay, groceries is done. So basically you get all your ingredient to cook your pizza. So when you have defined your recipe like this, then you could give it to Baker, and Baker, what it does, it do some compile time validation. static analysis, and derive this graph, a Petri Net graph. But this, in this case, it's not a Petri Net, so it's a graph of steps. So in this case, it's also draw all the flow relationship among this structure. It's quite similar to Petri Net, only we have additional construct event, but that's equivalent to cold transition in Petri Net. Just to give you an example, we had previously these 3 different services, and now would like to create a recipe to create an account, a current account at IG. How we can do that? We can define different interactions, and we can give it to the recipe, create a recipe from it, and give it to the recipe compiler. When we give it to the recipe compiler, it can sequence all the actions that need to be done. For instance, first you need to have the IBAN number and customer, create customer, that has to be done first. And then when you have the IBAN and customer ID, then you could do open account. And then when the account opening is done, you just notify your customer. So what's happening that we previously had all the transitions, now we have interactions. We're giving it to the compiler, and compiler is generating all the flow relationship. But before generating it, also validating that your recipe is correct. If the recipe is correct, then we compile it down to Petri Net, and that Petri Net can be executed via the Azure runtime that we have built earlier, part of the presentation. So we can instantiate instance of Baker by giving all the implementation of the interaction and the recipe. So we give the recipe and we give the implementation, then it creates an instance of Baker. And when an instance is created, we can, and let's say that a customer requests to create an account, it creates a process. So from recipe, we're going towards process now. Recipe is just a description, and process is the runtime part of your recipe. And then we can initiate some external events, like groceries is done, kitchen tools are available. When that is available, when these events are raised, then it start executing all the steps one by one. So all the transitions start firing, and we could check that, okay, at what state our current processing is in by taking a look at all the events that's already been fired, and by looking at the ingredients that already provided in the system or generated from the system. There are several things that we get for free using this model. One important aspect is that the concurrency. Since we're using Petri Net as our underlying engine, we get concurrency for free. While recipe compiler generating this graph, it makes sure that the concurrent paths can be executed parallelly. And then we do have also synchronization automatically done there. Apart from that, we also define persistence in a quite generic manner. So we at bank, we have a lot of different kind of regulation and policies. So we come up with a generic way of encrypting all the data. So now the application developer does not need to worry about any kind of encryption. If you use Baker, Baker is just alive. If you use it, your data will be encrypted and stored in Cassandra, for instance. And we do have some unreliable services. So in that case, we also come up with a generic way of retry mechanism. So if one of your steps fails, then it can retry with a configurable retry strategies. So if you get back to, if you take a look at the technology stack, we're using Scala, Akka, and all kind of extension of Akka, like Akka's cluster sharding, Akka persistent for event sourcing, and Akka stream for processing all different kind of events. And in production, we're storing the data in Cassandra. And for the event processing or getting event from outside of the system, we're using Kafka as well. So in this case, it's important to know that every process, all the events that coming is handled by one actor, one persistent actor. So every process, we create an actor, and this actor will be receiving all the events from outside and process all the events as well by firing the interactions or transition in Petri Net term. So yeah, we come up with this abstraction, then we tried it in different systems as well. For instance, in this case, we built an order management system with with this Baker recipe DSL. And we also tried the creating the current account creation, the sequence diagram that I've shown. Okay. Oh shit, I have 5 minutes. So that yeah. Still, it looks scary, but the thing is that you don't need to handle those arcs, the flow relationship yourself anymore. It's been done automatically by the compiler, analyzed, validated by the compiler. So yeah, we have done. We have built quite some abstraction, but what's the gain? What's the profit from it? We can visualize not only the compile time version of a recipe, but also the runtime. So at runtime, the events which are marked green are already being executed. So we do have a monitoring tool that can view that at which state the process is in right now, and yeah, that helps a lot with the different processes. If a process is stuck, we know that at what level the process got stuck. And since the underlying technology that we're using is Petri Net, we could do a lot of analysis. For instance, we could do reachability. We could find out that, okay, these are the date transitions. These are not being executed at all, given the initial marking error. And then we can also check if there is any cycles in your graph. These are only to name few, but there are more analysis that can be done. For instance, we could do a liveness check, boundness check, and there are a lot of different kind of analysis that we can be done on this net structure. And we'd like to focus on other aspects as well, like for instance, the path traversal time. We could find out that how much time it's taking to go from path A to path B, and also find out some bottleneck that, okay, probably one of the interaction is taking a long time to be executed. So these are the things that we would like to focus in future. Also, we have shown you that the choice in Petri Net, it was non-deterministic, but probably we could use some heuristic to determine that which part of choice will most likely to be executed. So the last benefit that we get is reusability. We get a unified programming model by using DSL, and so expert and non-expert of a team is communicating the same language. We get a conceptual integrity. So not only in one team, but multiple teams is picking up this way of modeling processes. If we take a look at different variant of product of creating current account, now most of the interaction can be reused from one product to another product. So we have the building blocks, and we can compose those building blocks together to create many different processes. And these interactions are created in a reusable building blocks and shared in a shared repository. So the other team who is starting a new process, they can pick up these interactions and start building the recipe and processes from it. So in our opinion, that was a huge gain from this whole project. So what next? We'd like to model Baker as a service where someone can upload an external DSL and it can start processing those DSL in a serverless architecture. And we would like to try out some other formalism as well. And we'd like to focus on a project where we could generate the UI from this recipe DSL for our back office. And every year we get around 8 million calls in our back office for different processes. So if we can visualize what's going on and at which step a process is stuck, we could we could help our back office quite a lot. And the last but not the least, we'd like to focus on process mining as well. Basically, that means that we do have a lot of mainframe computer that has event log. So we would like to analyze the event log and derive a Petri Net from it. So that way we could observe the behavior of the mainframes that we already have at ING. So yeah, these are the few directions that we'd like to work on in coming period. So the key takeaway from it that, okay, this was just one problem that we have solved by using some mathematical formalism. But definitely we need to, we have other problems that we probably could solve by taking input from academic research. So we should work more closely. And with respect to this project, the learning is that, okay, raising the abstraction level a bit towards the problem domain helps a lot, and hiding complexity especially make it much more, much more adoption that we got from it is by hiding complexities. So now all the teams are communicating with the same concept. So we get some conceptual integration by using the DSL that we have developed, and definitely it increased our reusability and productivity as well. And last but not the least, I'd like to point out probably this is the main learning that I had, that we should always use lawful abstractions, which are correct by construction, and if it has the formal semantics, that means that okay, we could analyze it and we could come up with some nice property. We could validate the thing that we have written works, and then we can deploy it without worrying about the runtime errors, null pointer exception, and that kind of stuff. So we have already open sourced all the code that I've shown on the slides. This project is there in GitHub. Please have a look and give us your feedback that how we can improve. On behalf of the team who is working on this project, I'd like to thank you for joining this talk. And if you have any question or feedback, please let me know. Yep. 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 Yeah, we were thinking of trying out some other formalism as well, but no, it's just something that I saw a talk in the morning. I thought that probably it's quite interesting to model distributed system like that, and therefore I was thinking that okay, maybe we can try out. The point that I was making, that since we have a separation of model and you have different model to model transformation is going on, we could change quite flexibly one part of the model and try out some other formalism as well. Yep. Yep.
So this modeling of specifically making the graph, it's a bit similar to that with the arrow structure, which is you know, like the Haskell, you have a that class called arrow. Model like networks of.
Okay, so it can automatically derive that arrows as well.
Well, I think it's used for like programming to model like networks or stuff that's communicating. So it's running.
No. No, but it's a good pointer. I'll take a look. If there's something that we can do. Yes.
On the runtime, how do you deal with changes to the recipes to prevent?
Oh, we don't.
Okay.
At this point, we don't have that feature. Okay. So we were thinking of some way of. So basically, it's immutable structure. If you create a new recipe, it's a new process. So how does the old process and new process? There's a mismatch between the old and the new. But we have been working in this project for let's say last 8 months now. So yeah, these are the stuff that's in our roadmap to look into. So right now, around 10 teams picked up this model, and they will be modeling all their processes using this Petri Net and Baker. Previously, it was like all hand-drawn, all hand-written. Now they could at least, they don't have to deal with concurrency anymore, synchronization anymore. So these are the stuff that they're getting for free. Yeah. Yes.
So basically, you define the Petri Net, and then from the model, the system is orchestrated automatically. How does that work? Is that what the system does?
No, the thing in the beginning, I was pointing out that okay, we are moving towards the service microservice-based architecture. So those services are there running somewhere, So those are the building blocks somewhere running, pure functions, getting some input, giving you some output. So in the recipe, you define that hey, I'd like to communicate with this service with this value and get this as a result. So I'm giving something to the service and getting something from the service, and that resulted as an ingredient in the system or a token in the Petri Net. So we communicate with the service, get result, and provide that token in the network.
So yeah, Yeah, so then basically, there, there is something of the orchestration system from the model, right?
I'm sorry, I didn't get the.
So there is a model, right?
Here's a model.
And then there are things happening in the system, right?
Yes.
So what is the connection between the model and things happening in the system?
So the model, you define it abstractly, and then you use the compiler to compile it to Petri Net and runtime version of the Petri Net. So you have it running somewhere now. We are running it in Akka cluster. Okay. So basically, each actor, a persistent actor, is responsible for one process. So we have this request ID, one of the slides I was showing, we have this request ID, and via this request ID, with cluster sharding, it can always go to that one actor, meaning that that one actor is handling all the transitions and firing different transitions. We could also persist that, and because a process can run for multiple days, so basically we can persist and reboot the process as well from persistence.
So then my question was, so what happens if, because it's kind of a protocol, right? So things that should happen are defined. Mm-hmm. So what happens if there's a failure or something?
Oh, that's also model in, the graph grow really big because that was also modeling that. So basically it can, interaction can fire one-off events. We have that construct in the language. So it can fire like, okay, I have the account has been created, or account, we could not create account.
Newsletter next week.
Yeah, sure. So maybe, we could.